Hello, this is Virgile Goldberg, and this is my Lab 1 about objects in motion. So first, as an introduction, this lab will aim to establish experimental and simulation visual representation of Newton's first and second law of motion. Newton's first law of motion states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. This means that an already moving object will therefore not accelerate or decelerate or change directions if no force is applied on it. Hence, with Newton's second law of motion, which is F equals to ma, if force is zero, mass is non-zero, then the acceleration must be zero, hence the velocity does not change. Concerning momentum, if there is no force acting on a moving object, its velocity stays constant, and considering its mass remains constant from momentum equals mass times velocity, we can deduce that momentum will remain constant. This lab aims to establish the difference between real-life experiments where forces such as friction, drag, interact on the system, and computer-generated simulations which have ideal conditions. And we'll see that in real-life experiments, the surroundings does have an impact on the results. So here are a few relevant formulas. We can see that the final velocity is equal to the original velocity plus the net force over mass times the change in time. Because the net force will be equal to 0, we can see that the final velocity is equal to the original velocity. We can also see that the final position will be equal to the initial position plus the average velocity times the change in time, which is derived partly from velocity equals the change of distance over the change of time. So here is the tracker analysis of my experiment. You can see that there was a little trolley that was pushed on a rail with an initial impulse and then was led to, we'll say, drive on its own on an almost frictionless rail. This is the system, and the surrounding around it is the friction acting onto the trolley and the air resistance. So I tracked the trolley through its movement of the x displacement over time, which we can find here, the x displacement over time. We can also see that there was a slight fluctuation in the y value of y displacement. This is mostly due to the track being slightly inclined compared to the video, as the video was not filmed exactly straight on. So here are the results from my experiment. First, we can see here that we have the time and the displacement. We'll say on the positive x displacement, we can find the initial velocity. So remember, it's delta d over delta t. So delta d is the difference between those two values, and the delta t is the difference between those two values, and we get 4.62 times 10 to the minus 1 meters per second. Now, the average velocity can be found as the gradient of this line of best fit, which is, we'll say, very strong with an r-squared value of 0.9999, and the average velocity is of 0.4605 meters per second. Now, for the computer simulation, the initial position vector, x position vector, is 0.00279, because we can see that in this in the experimental value, this was the original displacement. Now we can see that the velocity does not change because there's no forces acting on it, but the position does change at a constant rate of 0.0462 meters per timestamp. We can see that this trajectory resembles this one, and that this graph somewhat resembles the one of the experimental values. Now, comparing those two, we can see that the simulation has a slightly higher average velocity of 0.62 meters per second compared to 0.4605 meters per second. This is mainly due to the fact that the trolley, due to friction and air resistance, did slow down towards the end of the track, giving a slightly lower value towards the end of the recorded data, resulting in a slightly lower velocity. We can also see that because the camera was slightly tilted, the velocity was not necessarily linear, we'll say, on a 2D plane. As an extension, we can ask ourselves, what if we inverted the axis x and minus x? Well, because the derivative is the velocity, then if we inverted the x and minus x axis, the velocity will become negative, because as we can see from this graph, the gradient would just be negative, a complete mirror from the x-axis of this current line of best fit. Now, what does it mean in terms of push and pulls and forces? Well, if it has a constant velocity, then all forces must be equal to zero, or at least cancel themselves out. But in reality, in the real experiment, the cart slightly slowed down due to friction and air resistance, which slightly decelerated the cart. Thank you very much.